Yeah, for giving me the opportunity to speak here and for organizing the seminar. Thank you for that. Yes. And I want to talk about hyperbolic boundary problems and also Carleman estimates. And well, and what somehow is the connection between them is in some way the estimates, so to speak. The estimate part from the hyperbolic boundary problems are of the greatest interest to me because they share some similarities with Carleman estimates. Now, Carleman estimates, on the other hand, have usually been talked about in the context of compactly supported functions at first, but then later boundary terms were included, and that even makes the similarity between these two topics a little bit larger. Okay, now, hyperbolic boundary problems, and there are different types, and you see them in my table of contents. So I will talk about symmetric hyperbolic systems, strictly hyperbolic systems, also about scalar hyperbolic equations, which fall a little bit into the second category, but I still like to distinguish them. Okay, now, hyperbolic system of first order looks somehow like this. So I consider hyperbolicity in t direction. So I have matrix coefficients, and I work in a space-time cylinder. So finite time interval, omega being a spatial domain, gamma its boundary, and I have basically time derivative, and I have space derivatives. These matrices are all n cross n. The vectors is an n vector. F is the right-hand side. There may be a lower order term, but that is not that important. So the characteristic polynomial, just to put down the ground game, is then the determinant of the principal symbol. And I call this system hyperbolic if this polynomial, as a polynomial in tau, which is the dual variable of the time, has real roots for all xi and rd and for all tx in the space-time cylinder. Okay, so I usually use initial data when I consider an initial boundary value problem, and I have boundary data. That will be a matrix function of t and x, which maps into the image of B. It shouldn't be an M, sorry, that's my typo here. And then with this boundary condition, I will try to solve the system. But before I will somehow define what I mean by symmetric hyperbolic, when all coefficient matrix in the principal part are Hermitian or real symmetric, and when the matrix in front of the time derivative is positive definite, then the operator is called symmetric hyperbolic. If all the roots of the characteristic polynomial, which I know to be real, if they are distinct, as long as the xi is not zero, of course, then I call the system strictly hyperbolic. Okay, example for this. Maxwell's equations are somehow the nicest example I feel for hyperbolic systems of first order, because it's truly a first order system. And it shows also a little bit, I mean, what's going on, because it is symmetric, because usually in classical physics, at least, the parameters, the epsilon and the mu, the electric permittivity and magnetic permeability, are assumed to be positive, definite, real symmetric matrix functions. Then I may have also a conductivity term in here. Sometimes it's at zero, so there may be a lower order term, there may be not. And then I have current densities. Of course, in classical physics, the F2 is usually zero. There's no magnetic current density, but there may be an electric current density. So this system is indeed symmetric hyperbolic. Now, what I want to say about this briefly. So if I write down the matrices, I see it actually pretty nicely. This matrix is symmetric. If epsilon and mu are positive definite, it's also positive definite. And due to the way the curl works, the curl operator, this is also a symmetric matrix. Then I call the system isotropic if epsilon and mu are scalar. That means these parameters don't depend on the direction. And in this case, the characteristic polynomial looks like this. And that means the 6 characteristic roots are 0 and plus and minus c over the radical of epsilon mu in each have multiplicity 2. So it's symmetric hyperbolic, technically not strictly hyperbolic, but this falls because the roots, how to say, have constant multiplicity. I call these kind of systems, they're called constantly hyperbolic. So they fall almost in the strictly hyperbolic category. On the other hand, if the coefficient matrices, epsilon and mu, are true matrices and not scalar multiples of each other, then the characteristic roots in tau will have variable multiplicity. And this is well known from from classical physics, from the Fresnel surface, right? So that's a kind of surface. It has 2 leaves and then they have 4 points in common usually. So Maxwell's system already, has this kind of dichotomy. It's a symmetric system. Certain versions are close to strictly hyperbolic, but then there's also the anisotropic case, which is only symmetric. So that means we will talk at first about the theory of symmetric hyperbolic systems, and that can be traced back to Friedrichs, who wrote a paper in 1954. And boundary conditions were then included by Lax and Phillips in 1960. So we assume now the boundary is either non-characteristic uniformly or uniformly characteristic. That means this boundary matrix, where I basically take the spatial coefficients and multiply them with the matching component of the exterior normal vector, this has, so to speak, constant rank, at least, yeah, independence of x. And x moves all over the boundary. So x and t, and because I have sigma as my cylinder boundary. So now I assume also it has n plus positive eigenvalues, n minus negative eigenvalues, and that is also constant when tx moves along the boundary. Then the null space of A is a subset of the null space of B, and the boundary operator has Lipschitz coefficients, and I call it strictly dissipative if it ranks matches the number of negative eigenvalues, and I have this kind of inequality, so to speak, that together with the boundary matrix, I get, so to speak, something positive, well, at least on the image of A. So now, usually, these problems are approached with an a priori estimate. So we'll look at this. We assume to have Lipschitz coefficients, Lipschitz boundary, lower order terms L infinity. Okay, I work with the regular function of H1, Sobolev space H1 as pretty common. I introduce a function which is pre-multiplied by an exponential and take the scalar product in L2 with V with this operator. And then I expand this, use a little bit of integration by parts and Schwarz inequality and get my estimate here. That's the preliminary estimate. And where I use also the case that B is strictly dissipative. So I get really a pleasant estimate, so to speak, U at final time in the space estimated. All norms are in L2. L2 norm over the space-time cylinder, a boundary norm of AU. So which can be, if A is, so to speak, has full rank, then this is, so to speak, the full trace of U. And on the right-hand side, basically the operator, which will be the right-hand side, the boundary operator, and the initial data. So perfect estimate, all norms are in L2. So that I feel usually is very pleasing with hyperbolic systems of first order. You can just do everything in L2. So, and gamma needs to be large enough, so that's the purpose we included. And then we have the following theorem, which is usually referred to as a strong well-posedness in L2. So this initial boundary well problem, right? Right-hand, differential equation, boundary condition, initial data, with data in L2 as well posed in L2. That means I get a unique weak solution, continuous in time, L2 in space, which is semi-strong. That means it's the limit of more regular solution and satisfies my estimate. So the third term is somehow of interest because that tells me some boundary traces actually exhibit higher regularity. And this is not implied by the, trace theorem in Sobolev spaces. Hey, the solution is only in O2. Yeah, so this is strong well-posedness. Now, a few words about the proof. So once I have the estimate, I actually realize I need it for the dual problem. This is basically Friedrichs' idea from 1954. I look at the dual problem and I can also get a dissipative boundary operator for it. Existence of the weak solution follows by soft methods. That means Hahn-Banach theorem and Ries representation theorem. Then I regularize my weak solution using tangential Friedrichs modifiers. And this way I get a sequence of more regular solution, and I can also regularize it in normal direction, at least in some components, and in all components if the boundary is non-characteristic. And then non-zero initial data I can include using the method by Jeff Rauch. He proposed it in 1972, actually in slightly different context, but that works also. And what is remarkable, this theorem is, so to speak, works rather well, even in the case of uniformly characteristic boundaries, which is, by the way, the case with Maxwell's equations. I will show an example of that in a minute. And also minimal smoothness operator and also the boundary condition. So they're both Lipschitz, and in certain ways, certain examples, I can go even under that, can even do less. So let's look again at Maxwell's system. So what I do there, so I have the system here, and I split somehow the vector E and H into three components, so to speak, one being like basically the eigenvector for or the eigenstate for eigenspace for the zero of the boundary matrix and negative and positive eigenvalues. The boundary matrix I can write as a difference of two semi-positive matrices. All this helps me to write down fairly general, strictly dissipative boundary conditions. So nu cross E, the turn tangential component of the electric field minus the tangential component of the magnetic field, and then a matrix O, which has spectral norm strictly less than C, times something rather similar. Yeah, this is, so to speak, the dissipative boundary condition. Of course, O could be zero. In that case, I would get what they call the transparent boundary condition, or this boundary condition in that case is also the first approximation of the Silver-Miller radiation condition. So that is even of importance in computations, because if I compute solutions for the Maxwell system in the unbounded space, I have to bound it somewhere, and then this boundary condition is somehow the best first order approximation of Silver-Miller. Okay, so now I can weaken this a little bit, just work with dissipative boundary conditions, not strictly. If I just say it should be non-negative, the sum, there is a square missing here, there should be b squared. And then I get, so to speak, also what they call often weakly well-posedness, because I cannot say anything about the boundary traces then. So the estimate is a little weaker, and also the existence theorem is a little weaker, but it follows the same pattern. Okay. So this is enough about strictly hyperbolic, or sorry, about symmetric hyperbolic systems. Now I want to talk a little bit about, well, just let me mention for Maxwell's equations, this boundary condition here, the zero conductor condition, how it's called, is dissipative, but not strictly dissipative. So it's comparable to the Neumann condition for the wave equation. So now I talk about strictly hyperbolic systems, and there it is more convenient to work initially in the half space. So, and then probably use local coordinates to change this to a domain you wish to work with. Then, I will work with this kind of a system, and because of the orientation of the normal, the boundary matrix is then just the negative coefficient in front of the derivative in D direction, and I assume from now on that the boundary is non-characteristic. Now I look at the following ODE, initial value problem for an ODE, where I take essentially the Fourier transform in all tangential variables and only keep the derivative normal in space direction. Yeah, so this is basically the AD coefficients. I could also write ddxt. Well, and I assume coefficients to be constant for now. This matrix for future reference I denote by G. And now I say the following, depending on where my initial conditions are. We know this, how this works in ODE. I may get exponential increasing solution or exponential decaying solutions or something in between. But I characterize the stable subspace as in dynamical systems as the set of initial data which will provide me a decaying solution. So exponential decaying solution, I just need L2. That's enough because that's the framework I'm working in. That is called the stable subspace. Then Hirsch observed in 1963, and that was probably the first work on general mixed problems for hyperbolic systems, that the dimension of this stable subspace is actually equal to a constant regardless how I choose tau and eta. Yeah, that follows from hyperbolicity. As long as gamma is positive, so this gamma is important here. Then, furthermore, he said the boundary condition satisfies the Lopatinskii condition if its rank is equal to the dimension of this space and its kernel intersected with the space is just 0. Yeah, that means essentially I can control all the exponentially decaying solutions. I can control them with the boundary operator instead of choosing initial conditions. And here for convenience, I just take tau, gamma, eta in the unit sphere, where, or hemisphere, the gamma should always be positive. That ensures somehow that that I'm moving forward in direction of hyperbolicity. So that is the Lopatinskii condition. And then Hirsch also has the theorem. So for constant coefficients only, explicit solution he can construct as long as the Lopatinskii condition holds. And on the other hand, it's an up and down vote essentially. If the Lopatinskii condition fails, then the initial boundary value problem is still posed. Okay, rather similar, but a uniform version of this condition was used by Heinz Otto Kreiss in 1970, where he basically says, well, I don't want to have just the intersection with the kernel being empty, I want it with an estimate. Yeah, so that is very similar. It's also called uniform Lopatinskii condition for obvious reasons. So if I have this with an estimate, and then once this is with an estimate, actually Kreiss was able to prove a theorem very similar to the one stated for the symmetric system. So essentially L2 well-posedness for strictly hyperbolic systems. Yeah, so strictly hyperbolic boundary is important non-characteristic. And again, the mixed problem is L2 well-posed, and here we have even equivalence, if and only if B satisfies the Kreiss condition. Yeah, this theorem is due to Kreiss and Walston, both papers in 1970, and initially only for 0 initial data, but non-zero initial data were added by Rauch. But it's important that it's C infinity. And as a matter of fact, I mean, Kreiss, it's actually writes it nicely in this paper. He says, well, essentially, I could also write down the solution of the problem, but I'm interested in estimates. And he does everything for constant coefficients. And at the end, he argues, well, all I did, I can also use, so to speak, variable coefficients, because what I do with Fourier multipliers can be done the most important positivity estimate with the just recently proved Sharp-Gordon inequality due to Lax and Nierenberg. Well, now the question, of course, is, I mean, here you need much more smoothness, and that means if you go to arbitrary regions, you need also C infinity regions. Now, this has been improved, but it has taken actually a while because it's rather technical. And eventually you can say it works also for constantly hyperbolic operators, like the isotropic max. Now, that's not a good example. So it works for constantly hyperbolic operators and boundary operators with Lipschitz coefficients. Yeah, important here is a work, the text, essentially a textbook by Chazin-Piriou, I think, where for the first time this theory is in book form, where they observed actually where Kreiss said he needs the sharp Gording inequality. With a trick, they managed to use just the Gording inequality. And that's important because that's pseudo-differential analysis, and sharp Gording, you cannot go beyond, I think, C11, whereas with Gording inequality, you can get it down to Lipschitz. And that was not realized here. That was realized in a series of papers by Matthias, first in 2000 to go from strictly hyperbolic to constantly hyperbolic, in 2001 to get Lipschitz coefficients. There he used the theory of para-differential operators, which is well adjusted to that. So it's rather technical work, but it goes through. And then was still the question open, what about the initial data? Because that was somehow more difficult in the constant hyperbolic case. And then in 2016, that was also clarified. So now I think the theorem is as good as it probably can get. Yeah, so Kreiss theorem on strictly hyperbolic systems. Now, I want to talk about something a little bit different, namely what can happen, so to speak, with the Lopatinskii if the Kreiss condition is violated. I said with the Lopatinskii condition introduced by Hirsch, it's basically an up and down vote. Now there's actually something a little bit in between, which we see when we look at the forward characteristic cone. You can just think about the wave equation. That's actually fine. You can reduce the wave equation to a strictly hyperbolic system, where basically the forward time vector, so the t component, tau component is the first one. Hyperbolic region is basically then the extension that is one dimension less, because the normal direction to the, the xt direction normal to the boundary is missing. That this matrix with gamma equals 0 is diagonalizable, still has real eigenvalues. So maybe not too far away from the, so the tau basically dominates eta that is needed for that to be hyperbolic. And it is known this kind of, yeah, what is this now? That's here, in this here region, the stable subspace, which is the subspace we used for the definition of the Lopatinskii condition and the Kreiss condition, has a real basis. Well, so this is just to put a little bit something down. Now, just a picture, also some things we need later on. So here is the characteristic cone, and the forward characteristic cone is just, so to speak, the upper half. Yeah, I should have written tau here, C0 for maybe future purposes. And here, then there's always the dual cone, right? If I have a hyperbolic, second order hyperbolic operator, then here I have the coefficient, so to speak, of the symbol. Here I have the dual matrix or the inverse matrix. And then I use T and X here as components. Then also, just for future reference, the time-like vector is inside of the, what they call the ray cone. A space-like vector is not. So then we can now distinguish three classes of initial boundary value problems. That's a work by 4 French mathematicians, about 20 years old. So strongly stable, well, what we just talked about, the Kreiss or Kreiss-Sakamoto condition, because Sakamoto established something similar for scalar equations, holds. Unstable if the Lopatinskii condition fails. And now very interesting, there's, so to speak, something in between, weakly regular of real type. Lopatinskii condition holds, but okay, the uniformity, here written basically this L for, I can write it also as a Lopatinskii determinant, has zeros only in the interior of this hyperbolic region here, R, which I had here, hyperbolic region. Yeah, so that's where zeros are allowed, only in the hyperbolic region. And the interesting thing is, so to speak, and that is something was even missed by Kreiss initially, that these classes are all open, in the sense that if I have an operator with boundary, the boundary condition, And if I move the boundary, the coefficients in the boundary or in the operator a little bit, it stays in this. Yeah, it stays in this. So strongly stable, then stays stable, and so on. And this also. And now, little example about this. What would this be? The scalar wave equation, when you have, so to speak, here the normal derivative, and then you have, oh wait, that's the U is here superfluous, that shouldn't be there. Then you have an inner product between a vector field and U. And this should be the gradient here. Sorry, should be the tangential gradient. Then this is, so to speak, and B is a space-like vector that is weakly regular of real type. Yeah, that means you have the Lopatinskii condition satisfied, so you have a C infinity solution, at least with constant coefficients. Probably you can also do it with variable coefficients, I believe. But there's no guarantee of any estimates. Yes. And then a conservative boundary condition, such the Neumann doesn't fall in any of these classes, but as soon as you perturb it a little bit, you can move in any of those classes. So if I add a little bit of a t derivative here, I can make this stable. If I subtract a little bit or vice versa, then I make it unstable. And if I add a little bit of a spatial derivative, I make it weakly regular. Yeah, so that are these weakly regular of real type problems. Now, a few words about strictly hyperbolic equations. Yes, this was a theory developed in parallel by mainly by Sakamoto, who wrote a very nice book about it. I mean, in 1982, it's actually self-contained, very good description. So, and similarly to the, how shall I say, stability of the stable subspace, here you have essentially the factorization of the principal symbol. As soon as you basically complexify the dual variable of the time, you can then factor this smoothly. Yeah, those polynomials have always the same order, and you can even extend it to gamma equals 0 degrees independent. Then Sakamoto's condition, essentially the analog of the Kreiss condition, that the principal symbols of the boundary operators considered as polynomials in CD modulo P plus, yeah, they have to be, so to speak, linearly independent. Yeah, that's this in here. So they should be linearly independent. And then an analytic way of writing this is, so to speak, that the so-called Lopatinskii determinant should be non-zero, and that should be extended up to gamma equals 0. So this is a general theory that's actually pretty formidable. What I felt was interesting, and what I realized actually only recently, I think, during the pandemic, that Gording, he wrote a very short paper in the Compte Rendu, so it's, I guess, only supposed to be surveys, on 2 pages, where he says, well, if you use the wave equation with variable coefficients and you use the first order operator, where it should be here b of x, this vector b is in the forward light cone. So that means it's a time-like vector, yeah, according to our picture. Then you get actually this well-Posendus estimate. Now, if you have scalar equations, they're always, I mean, second order energy space is H1. So you get a little bit more things in there, but you can still probably see it's very similar to this well-Posendus estimates for this, for the symmetric hyperbolic systems. So it's very similar to that. And you essentially also get trace regularity, the Dirichlet trace in H1, the Neumann trace in L2 as it should be, initial data, final data, final velocity function, and then this is bounded by that. Here's the boundary data and the initial data. So perfect estimate, and you can use this somehow to prove well, strong well-Posendus in H1 for the wave equation with a first order boundary condition. And Hermander actually did the same. He writes it in his book for the Dirichlet condition. So what I like with these results, they don't need any microlocal analysis. They're actually done with integration by parts only. So this way you can obtain these estimates. Now, what I still want to do before I turned over to go to Carleman estimates, I want to say something about, the comparison of the theory of strictly hyperbolic systems versus symmetric hyperbolic systems. Symmetric hyperbolic system with strictly dissipative boundary conditions. It works also well for characteristic boundaries. We emphasized this already, and it's important for something like Maxwell's equations, for instance. It's also important if you try to, so to speak, start with a scalar equation and you make a symmetric system out of it, because usually if you do that, you add characteristics to it. So there's no way around it. So that's why it's good. This theory is fairly flexible. Then there's this paper by Maida and Osher from 1975. They extended Kreiss theory to the case when the boundary is characteristic. However, they need as an assumption that the system is symmetric, otherwise it doesn't fly. Yeah, so even then, if you try to use, so to speak, Kreiss approach, then you still need symmetry. And things actually are pretty bad if you have, so to speak, even strictly hyperbolic, but you don't have, so to speak, symmetry, or you cannot get it easily. Lately, and this ties almost a little bit back to the talk last week, to Barbara Kaltenbacher's talk. She talked about the Kuznetsov equation, and I feel like the more Gibson-Thompson is probably a linearization thereof. So that's a third order, strictly hyperbolic PDE. And of course, if you consider that in a finite and bounded region, the boundary cannot be non-characteristic. That's pretty much impossible. And there have been some work also on non-homogeneous boundary value problem. Yeah, that's the interest when you consider these theories, to consider non-homogeneous boundary data. If the boundary data is zero, you can use probably semi-group theories and things like that. And we did here rather recently a paper on the Dirichlet condition. And it's actually, yeah, we expected, okay, you lose probably some boundary traces in the estimate and things like that. But we even lost some interior regularity. So that was, and also the regularity of the boundary data had to be carefully adjusted. We have to admit, as Trigiani in 2018, essentially you don't prove an estimate from scratch here. You go back to the wave equation because you see the principal part, basically, which is the third time derivative, and here the third derivative, Laplacian ut. That is just the time derivative of the wave operator. And those are lower order terms. That's where actually strict hyperbolicity is really useful, because it says basically everything of lower order is a truly lower order term and cannot interfere in the analysis. Okay, so that's much about characteristic boundaries. What I also want to say is now compare, so to speak, in some way, I have the feeling, symmetric hyperbolic systems occur actually rather often, not only Maxwell's equations. Another example of it, even though it's second order, is the linear elasticity, right? And in particular, if you have anisotropic media, then it's not strictly hyperbolic. So on the other hand, the Kreiss-Sakamoto condition is somehow more sophisticated than the strictly dissipative condition. In particular, Kreiss-Sakamoto, I didn't do this here, but you can also make it easily non-local. Yeah, because you do it actually in the Fourier variable. So, and that has been used by the analysis of shock waves, which has basically also driven a lot of this progress in the French school by Métivier and his collaborators. So, but an interesting result here by them is the following: boundary value problem, non-characteristic symmetric hyperbolic system with constant coefficients and boundary operator which satisfies Kreiss-Sakamoto is well posed in L2. So you can essentially use the Kreiss-Sakamoto condition on symmetric hyperbolic. There's no strict hyperbolicity or constant hyperbolicity required here. Yeah, and it comes from that fact that the definition of the Kreiss condition doesn't require strict hyperbolicity, so you can actually use it. So that's kind of interesting. I extended this to characteristic boundaries and the Vega version of the Kreiss-Sakamoto condition, which is sometimes useful for like Neumann conditions, or even for these kind of oblique derivative conditions. But interesting enough, in 2017, Métivier constructed a symmetric hyperbolic system, this time with variable coefficients, and a boundary condition of Kreiss-Sakamoto type, and the problem fails to be L2 well-posed. Yeah, so it can actually go wrong. There's a difference between variable and constant coefficients here. And of course, in constant coefficients, you can use the Fourier transform directly. Their analysis is much easier. But that means, so to speak, you cannot push it all the way, which also, I think, I mean, it's an interesting detail here. So it's really a rather sophisticated theory. So it's few words just, yeah, because I mean, just to show, I mean, how sophisticated this theory has involved. What is about the Neumann problem, right? Miyatake in 1974 already showed, I mean, you have well-posted in the finite energy space, H1O2. With boundary data, you have to make them a little bit higher regularity than H1. Then Laszewski and Trigani actually used L2 Neumann data, and they work in control theory, so they're in particular, I mean, interested in, yeah, L2 inputs, L2 controls, and yet you actually produce a solution which is a little bit higher, H3/5 minus epsilon, right? So that's a little bit goes, this would be the analog would be 1/2. So it's a little bit more regular. And then the probably, I mean, the final result, which is probably the best possible, is Tataru's result from 98. L2 Neumann data produced in H2/3 U. So it's just a loss of regularity of 1/3 and Dirichlet trace in 1/3. So that is somehow a little better. And this result has had some significance in control theory. And even you can even get a little better result. So if locally the boundary is pseudo-concave, then Neumann data give actually a solution even in U⁵. Yeah, and then the Dirichlet trace is also a little better. So the geometry of the boundary will matter then. So that means it depends really on the micro-locality there. Okay, so that was my part on hyperbolic systems. Now a few words about Carleman estimates. So generally, look at first at partial differential operators, scalar partial differential operators of order m with C1 coefficients. On the principal part, if I have a strongly pseudo-convex function, then I can prove this kind of an estimate where I have here the weighted m-1 norm. And here I have, so to speak, on the right-hand side, the norm of the operator. And this is true for compactly supported function for a large enough parameter. I have to say here now, from now on, I use the tau not as the dual variable of the time, but rather as the large parameter in the Carleman estimate. So a little bit like the gamma was before. I just have, I mean, followed the traditional notation, and I didn't feel like I could change this for this talk. So now Carleman estimates were usually used to prove unique continuation for operators with non-analytic coefficients. Because for analytic coefficients, you have Holmgren's theorem, which is somehow probably the optimal result. However, in order to get useful results in regard to unique continuation, something similar to Holmgren's theorem, then you need actually quite a bit of pseudo-convex functions. And my impression is somehow that, yeah, only for second order scalar operators, you get enough pseudo-convex functions. So like for the second order wave equation, with adjustment also for parabolic or Schrödinger equation, for elliptic equations, there's no problem. And then also for some elliptic systems. But as soon as you try to use it for higher order equations, it actually doesn't work this well. And as far as I can tell, most results for higher order equations or also other systems have been obtained by iterating Carleman estimates for second order equations. So that's why I will focus now on the second order case. And while, so to speak, for unique continuation, I'm perfectly happy with using compact support. This will work great. But if I want to use these estimates directly in boundary control or also maybe in inverse problems, then I may need boundary terms. And there's this result by Lebeau and Trobiano I think proof for a second order operator with smooth coefficients that you can actually include the Dirichlet and the Neumann trace, and then you can just do it for any u in H2, so you don't need to have compact support. And moreover, you can work, so to speak, even with the Dirichlet trace alone if you have a condition on the weight function. Of course, this needs to be, the weight function, of course, needs still to be strongly pseudo-convex. Yeah, I will not emphasize it. So it puts quite a bit of conditions on that, and it's impossible to satisfy this in the whole domain. So that's why it's right here just the intersection. So it's only then a local estimate somehow. Yeah, and here, yeah, so I can also recover then, so to speak, the Neumann trace here. Well, now, this is Lebos and Robiano's result, including traces, and also doing something special if they have only the Dirichlet trace. This estimate, you see already, is rather similar to the estimate in hyperbolic, a priori estimate in hyperbolic problems. Okay, I don't have initial data here, but if I cut those out, it is actually very similar. And I feel also for Carleman estimates, what you can say, you basically try to propagate in direction phi prime or negative phi prime, essentially. Yeah, so that is, so to speak, you consider them, the problem a little bit as an evolution, even though you don't, even if the problem is hyperbolic, this may not be the direction of hyperbolicity. So there's also some conflict in it, but you essentially consider your equation as an evolution equation in direction phi prime. And then you see these estimates are pretty similar. Well, Tataru made out of this in a very general result. Yeah, also for operators of order m, so you got a very general result and introduced a condition which he called the strong Lopatinskii condition. And this condition is actually a rather tough cookie because the polynomial or the symbol which matters is, so to speak, like in the hyperbolic case, just you don't propagate in direction t. So you have now this propagation in direction phi prime. This factorization into roots, which have positive and negative imaginary part, is not smooth. Yeah, so that is actually rather forbidden here. So you don't have, as you have for the Kreiss or Sakamoto condition, you don't have the smooth factorization. On the other hand, one should also say the rank condition in the hyperbolic estimate is actually not necessary for the estimate, it's necessary for existence, so that everything is in balance. Here, you can, of course, always afford to throw in more boundary operators because you just care about uniqueness. You just compare about the estimate. And you know, I mean, you cannot use Carleman estimates, I mean, to establish somehow existence of the ill-posed Cauchy problem. So that actually doesn't work. So it's only for uniqueness. That's why this adds a layer of technical difficulty, but it's somehow almost expected because you cannot somehow use that then to prove existence. Now, I want to look a little bit at the second order case, because I said already regarding Carleman estimates, the second order case is somehow the most interesting. And there we introduce semi-geodesic normal coordinates. And then I can, so to speak, put on the normal derivative with coefficient 1 and put everything else into a quadratic form. And I factor the polynomial in with respect to the normal variable here. And I have then two zeros which look like this. So again, I can work with homogeneity reason. I fix a boundary point. I can again work with the upper hemisphere here. And now I factor as long as tau is positive. The factorization is actually rather straightforward as long as I order my roots a little bit. And of course, I'm interested in just placing roots with, positive imaginary part into, so to speak, this polynomial, because then because then I expect that I get exponential decaying solutions. So that is okay for positive tau. I can actually do the factorization rather straightforward, but for tau equals 0, actually all hell breaks loose. I just show you this briefly. It's actually pretty terrible because I always try to see, well, what happens now if I change tau to slightly positive? In which way does my root go? Does it get positive imaginary part? Does it get negative imaginary part? So that's what I try to decide. And once I have this, well, I understand how this polynomial works. I can define the, this what Tataru calls uniform, strong Lopatinskii condition. I prefer to call it actually Sakamoto-Tataru condition because I feel also Tataru deserves credit for this condition because it's a little different. So if this polynomial here, which I just defined as a polynomial in CD, is at most of degree 1, and those guys are linearly independent as polynomials in CD. Then I say this boundary operator, which is again my first order operator with real coefficients, that I have this condition satisfied. Now, following proposition, because I need to control the degree of this polynomial. That's not a given. In hyperbolic theory, this is perfectly fine, but now with Carleman estimates, this is actually difficult. Now, this is of degree at most 1, if either the normal derivative or the inward normal derivative is positive. That's really this condition already shown by Lebeau and Robiano, essentially. Or if it's hyperbolic in a direction orthogonal to the boundary. That means it's essentially the setting of the hyperbolic problem, which is somehow worked in here because I can choose the phi any way I wish, right, in principle. So that means then it's of degree at most 1. It's also of degree 0, but that case is not very interesting. That's essentially the case if the boundary is like a final boundary in the space-time cylinder. Yeah, then of course for hyperbolic problem, I don't need any final conditions. Yeah, that's nothing new. Then I have degree 0, then I don't need any boundary conditions. So the second part is in that way pretty clear. Now, if my operator is elliptic, then in the case tau equals 0 does not create extra conditions. And I can just say if P is elliptic, then this first order boundary operator satisfies the Sakamoto-Tataru condition at the boundary point if and only if those two conditions hold. So the normal derivative of the pseudo-convex function needs to be negative, and I need this condition. Now, the case tau equals 0, which I showed you only briefly, fortunately, one managed just to simplify it and write it actually rather neatly. Sakamoto-Tataru condition at tau equals 0 is satisfied if and only if. At a point where both the symbol of the boundary condition and the operator, both 0, imply a condition on the Poisson bracket, pre-multiplied by XCD. This is a condition which is essentially already invariant because I can actually express the XCD also in terms of a symbol. So I wouldn't even need the special choice of coordinates. Yeah, so that's actually quite useful. Whereas for the formulation, it's probably really better to use specially chosen coordinates for the definition of the Sakamoto-Tataru condition. Then, now for hyperbolic operators, what can I say? The first statement here is actually essentially just the problem for the hyperbolic system, just that I don't use as my function phi as I use it for the hyperbolic problem negative t. I use something a little bit more general, but I still basically a time-like vector field, phi prime. And then I get basically the condition which Gording already pointed out. Yeah, it's a little bit more general, but it's essentially what Gording did in 1977. And now, if it's hyperbolic, but not in direction of the boundary, but not in direction phi prime, that's actually what I'm interested in boundary control, or when I talk about unique continuation, because I want to have it for an ill-post or lateral Cauchy problem. Yeah, then I need basically certain conditions. Either B is time-like, and this condition makes basically sure it's in the, however I call it, forward cone. So it's only in one side of the time-like cone. On the ray cone, then also, that's also okay. So it doesn't need to be strictly time-like. Space-like, then I get additional conditions. Basically, still the tangential component of B has to be time-like. So, and then another vector has to be time-like. The linear combination of B and the gradient of B, whereas the gradient is essentially the vector field corresponding to the covector field phi prime if I use the pseudo-Riemannian metric here to decide this. Yeah, but this is good. And I was looking for conditions like this because I wanted to have it invariantly, so to speak, that it doesn't depend on the choice of coordinates. Still, this is a complicated condition. And the results, the examples I can give with them, they are not too satisfying. So, but it clarifies indeed that the Neumann condition for elliptic operators, that goes back to the slide before, satisfies the Sakamoto-Tataru condition. If it's hyperbolic in this direction of propagation, Neumann condition doesn't satisfy Sakamoto-Tataru condition because it's essentially just Sakamoto's condition. But here also, if it's hyperbolic but not in direction of phi prime, so what I'm interested in unique continuation, then the Neumann condition does not satisfy the Sakamoto-Tataru condition. But we know also essentially as for the, dissipative boundary conditions, yes, but not strictly dissipative boundary condition, I can get an estimate which has been known for a while. So for a while, then people were looking how to construct like pseudo-convex functions which somehow satisfy this on a large portion of the boundary. Okay, this is pretty much it. Thank you very much for listening. Thank you.
Thank you very much, Matthias, for the very nice talk. Thank you very much. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself. Any questions or comments? Okay, if not, thank you very much, Matthias, for the very, very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you very much. Thank you.